In this example 6, we're going to see that all is not, rainbows with continuity. There are points of discontinuity, and in particular, the principal square root. So whenever you write z to the 1/2 and you think about it as a function, you mean the principal square root. We're not returning more than one value, just the principal square root. We're going to see that this guy is not continuous at -1. Now, before we do the argument, let's go in and let's show why. Geometrically, why can't it be continuous? So the domain here in our z-plane is everything. And then the codomain is also everything. So what was I using? I think here's our W plane, our output plane. And what happens when you take the square root of something? Well, a point, say here, is going to get moved closer to the origin, if this is, say, further than 1 away, and it's also going to have a halved argument. So it's going to move to somewhere like over here. Whereas a point down here at B is going to move sort of the opposite way. So it's going to get halved, and then all of the outputs are going to be within the first or the fourth quadrant, because when you half their argument, you get -π/2 to π/2. And it's going to be maybe something like here, b to the 1/2. What is happening in our function? The following thing is happening. The points on the negative real axis and above in the second and first quadrant, they get moved, they get shifted, they get rotated and modulus rooted. They get moved to the right, whereas points below get moved in the counterclockwise fashion. So they get moved that way. So what is happening here is we're ripping open the complex plane along this gold line. So z to the 1/2 rips open C along the real part of z is less than or equal to 0. Just rips it up. And when it rips it up, that gold line is going to go here, and then this is going to be a dotted line. Those are non-inclusive. So it rips and tears, which is why it is not continuous. Geometrically, why it is not continuous. So how do we prove that? Well, we're going to look at some limits. So if we mark our point -1, we can approach -1 along, let's see, what's easy to compute the square root of? Something like a circle. So we're going to approach along e to the I theta, which is going to be a kind of positive approach path, a counterclockwise approach path. And then we're going to approach along e to the -I theta, which is a clockwise approach path. Okay, so our e to the I theta approach path is going to, we're going to plug that in, and as theta goes to pi, the points on our curve are going to go to -1. Okay, so let's look at that approach path. So we're going to look at the limit as theta goes to pi, e to the I theta to the 1/2. So that's the limit theta goes to pi, e to the I theta over 2. This is we haven't proved this, but the exponential function is a continuous function, and we can just plug in our pi. And that is a principal argument of 90 degrees, and so we get I from that. All right, now we're going to go along the other approach path, so e to the -I theta, and it's still the same. As theta goes to pi, this goes to e to the -I pi, and -I pi is, e to the -I pi is -1 still, but we're approaching along a clockwise arc. So we're going to look now, limit theta goes to pi, but instead of going counterclockwise, we're going clockwise. And so that's limit theta goes to pi, e to the negative I theta over 2. And that's e to the negative I pi over 2. That's an angle of negative 90 degrees. That points directly down, and the modulus is 1. And we see our limiting values are different. I and negative I are not the same. So we have two different approach paths, two different arcs that give us different limiting values. What can we conclude? Well, the limit as z goes to negative 1, z to the 1/2. Well, it doesn't even exist. So z to the 1/2 cannot possibly be continuous here because the limit doesn't exist. Let me just note, though, that negative 1 to the 1/2 does exist, and it's I. That's the definition of I, right? It's just that the limiting value doesn't exist. Okay. Now you can fix this. How can you fix the failure of this function to be continuous at points? Well, you can do what's called a branch cut, and you can remove that negative real axis. So if instead, this is just a note. If we changed the domain of z to the 1/2 to be c minus the negative real axis. Actually, we want to get rid of the non-negative real axis, so the z is such that the non-positive real part of z is less than or equal to 0. Then z to the 1/2 is continuous on its domain now, because we got rid of that point where we've ripped open the points where we rip open the complex plane. And this is a domain in the sense of chapter 1. We've gotten rid of the closed set where the real part's less than or equal to 0. That is, we're looking, well, this is a closed set. This is not quite right, actually. Sorry, let me fix this slightly. So it's going to be, sorry. Let me write it how it should be. Sorry, this should x plus 0i, where x is less than or equal to 0. That's what I'm trying to accomplish here. We want to get rid of that real negative, non-positive real axis. That's how we do that. And this is a domain in the sense of chapter 1. It's an open set, and it's connected. Because all we're doing is we're coming in, and we're snipping out that gold line, and what's left is open. There's wiggle room at all points.